Going to let A equal x centimeters and B is going to be, now here's something important. We know that when these pulses superpose at point P, it causes a destructive interference. Now, how we achieve a destructive interference is if one pulse has a crest and the other pulse has a trough, meaning that one has a positive amplitude and the other has a negative. So if we're taking A as being positive, let's take B as being negative, and we were told that B is 3 times larger than A. So B is going to be negative 3x centimeters. Now at point P, these two pulses are going to add together, so we have A plus B that is going to give you P. So A is x, B is negative 3x, and point P was given as, it says, where they form a trough with an amplitude of 6 centimeters. Since they form a trough at point P, P is going to be negative 6. Now let's simplify. On the left we have x minus 3x, which is negative 2x. On the right, negative 6. Divide throughout by negative 2 to get x alone. So x is actually 3 centimeters. But remember here, x represents A. That is not what the question wanted. The question wanted the amplitude of B. So B was 3 times x. So it's going to be 3 times 3, which is 9 centimeters. Now, for the sake of the calculation, we had to make B negative. But when we talk about amplitude in general, we take it as a positive value. It's just that when it comes to destructive interference, we need one value to be positive and one to be negative, which is why we took B initially as negative 3x. But when you're actually calculating the amplitude itself, you can keep B as positive, that's fine. Amplitude is taken as a positive value. Now 2.3 says write down the wavelength of the pulse at point P. So if you haven't noticed, wavelength was given to you. They mentioned that the pulses have a wavelength of 5. Now wavelength is not affected during superposition. So no matter what the wavelength initially was, it stays like that throughout the motion of the pulses. Even when superposition occurs, it stays unaffected. That is why it's only 1 mark, because wavelength would still be 5 centimeters. Now 2.4 says draw the pulses after they pass point P and label each pulse clearly. So here's what's going to happen. We had A moving to the right, we had B moving to the left. Once they pass each other at point B and once superposition occurs, they continue moving in their original positions. So pulse A will continue moving to the right and pulse B will continue moving to the left. So here's what this is going to look like. A is moving to the right, B is moving to the left. And remember that whatever A was, B was 3 times that. Since we took A as being positive and B as being negative, you can see that A here has a crest and B has a trough. So all of that needs to be evident on your diagram. So here's question 3, and this is now testing you on longitudinal waves. 3.1 says the distance between points P and Q is 0.3 meters on the wave pattern shown below. And the speed of the wave is 1.5 meters per second. We kind of already answered the first question. Is the above wave transverse or longitudinal? So yeah, we know it's longitudinal. 3.1.2. Write down the names of the sections of the wave labeled R and S. Provide the letter and next to it the correct name. So when we look at R, we notice that these lines are now closer together. These are known as compressions. And where we have S, where our lines are spread apart, those are known as rarefactions. So let's write that down. R is a compression and S is a rarefaction. Now 1.1.3 says calculate the wavelength of the wave. So what does wavelength represent? Wavelength is the distance that it takes to make one wave. And we are given a distance on our diagram. We are given a 0.3 meters. But what we notice here is that this 0.3 meters covers two waves. How do we know it covers two waves? So notice where our wave starts. We are starting from the beginning of a compression. So from the beginning of one compression to the beginning of another compression, that is one wave. From the beginning of this compression to the next one, that is another wave. So this is representing two waves. Now, if 0.3 meters covers two waves, wavelength covers one wave. So don't we just have to take 0.3 and divide by 2? But that's exactly what we need to do. So let's write that down. So remember, wavelength is represented by lambda, and 0.3 divided by 2 is 0.15, and wavelength is always measured in meters. Now 1.3.4 says determine the period of the wave. So just a quick reminder of your formula for period. Period is 1 over frequency, but we actually don't have the frequency. However, we can calculate it. Seeing that we know the distance of, if we're going to work with one wave, right? We know the distance and we know the speed. We can use speed is equal to distance over time for one wave, and that would give you period. But what I actually want to use is speed, v, is equal to frequency times lambda. So I want to show you that formula. So here's the formula that we have. Speed was given to us, right? V is speed, that's 1.5. Frequency is what we need, and we just calculated lambda, which is 0.15. Now here we can calculate frequency, and doing so, we should get 10 hertz. Now, since we need to calculate period, we know that period is equal to 1 over frequency. So we've got 1 over 10, and therefore period is 0.1 seconds. So this was a two-step process. We calculated frequency first using the speed that was given and the lambda that we calculated, and then we went on to using the period formula. It's 1 over frequency, so we had 1 over 10 and 0.1 seconds as our answer. Now here's 3.2, and it's based on new information. It says the diagram below represents a wave moving from left to right. The distance between points B and G is 1.2 meters. So B is a crest, G is a trough, so all the way from top to bottom is, or actually, sorry, that is horizontal. They've given you both. They've given you the horizontal distance and the vertical. So horizontally from B to G is 1.2, but vertically from B to G is 0.2. It says 2 complete wave cycles pass point B every second. That makes sense. We can see clearly that this is 2 waves. Now the first thing they want you to do is write down the amplitude of the wave. So amplitude always goes from your equilibrium position. So that's your point of rest. And it goes from that point to the highest point. Now, since we know the distance between the crest and the trough, which is 0.2, amplitude is going to be half of that. So 3.2.1, amplitude is 0.1 meters. 3.2.2 says identify a point that is in phase with C. Let's just locate C. So remember, points that are in phase are points that are at the exact same position on each wave. So the point that will be in phase with point C has to be point F. Because notice, on each separate wave, they are at the exact same location. 3.2.3 says identify the term frequency. So frequency generally is how many waves are created per second. Or we can say the number of wave pulses per second. What I have noticed is that the frequency definition usually comes in many different forms across different past papers and their memos, where they all state the same thing, but with the use of different words. So some of them say the number of waves passing a certain point per second, which is also correct. Or how many waves are created per second, or how many waves are passing through a certain point per second. Or like this, the number of wave pulses per second. All of which are correct. They are saying the same thing. Now it says calculate the time taken for the wave to move from point B to point G. So we want to know the time taken for the wave to go from this point, point B, to point G. Basically, how long is it going to take the wave to travel that 1.2 meter distance? So here's the thing, right? We know that we have two waves created here. Let's focus on trying to figure out how long it takes for one wave to occur. Because if we're able to do that, if we can know the time taken for one wave to occur, then it's quite easy for us to calculate the time for this wave to occur from B all the way to G. So what information do we actually have? They gave you something very important at the bottom. 2 complete wave cycles pass point B every second. What is that? The number of wave cycles passing through a certain point per second, that is frequency. So they didn't explicitly say that, hey, the frequency is 2, but instead they gave it to you in the form of the definition. So let's start there. I'm going to use this frequency and I'm going to calculate period. Here's our formula. Now let's substitute. So we have 1 over 2, and 1 over 2 as a decimal is 0.5, which means that the period is 0.5 seconds. Now what does period mean? Period is how long it takes for one wave to occur. So let's go back up to our diagram and let's count how many waves we have from point B to point G. Now since we're starting off here at point B, from point B, which is a crest, to the next crest, which is point E, that is one wave. From E to G, that is half a wave. So from B to G, that's only 1.5 waves. So since we know the time for one wave to occur, if we want to know the time for 1.5 waves to occur, we just need to take 1.5 and multiply it with this period. So here's what we're going to have. 1.5 times 0.5. That is going to give you 0.75 seconds. So that is how long it takes for the wave to move from point B to point G. We're now on to question 4, and this is an extension of waves, but it's tested as sound. So it's everything to do with sound, its applications, its uses. We cover ultrasound as well as echolocation. Okay, so 4.1 says the average human ear can hear sounds up to a frequency of 20 kilohertz. So remember, 20 kilohertz is the same thing as 20,000 hertz. Bats can detect frequencies of up to 200 kilohertz, using this adaptation to navigate. They emit high-frequency sound waves and detect the echo. A bat flying at a constant velocity of 3 meters per second due east emits a sound wave when it is X meters away from a wall. The sound bounces off the wall and the bat detects the echo 2 seconds later. During this 2-second interval, the bat continued flying due east, covering a distance of 6 meters. Take the speed of sound in air as 340 meters per second. So it's really important that you read all of this information carefully because there's quite a bit given. All of your values are given in here, as well as the motion of this sound source, where the bat here is a sound source because it is emitting the sound. Okay, so we see that the bat is going east. There's the bat going to the right. 4.1.1 says define the term echo in words. Now, an echo is a reflection of sound waves. Basically, what happens is the sound travels, and when it hits a barrier, it changes direction and it travels back towards you. That is how sometimes if you are in a very empty room or you are at the top of a hill, you have to speak very loudly or clap your hands very loudly. You may hear the sound come back to you after a while. That's what's known as an echo. Basically, your sound waves travel, and as soon as they hit a barrier, they are reflected off the surface of the barrier and they return to you. So, an echo is a reflection of sound waves. So in order for you to get the distance between the bat and the wall, let's first refer back to the information given. And let's understand the situation. So the bat is flying to the right, the bat is going east. When it is X meters away from the wall, that is when it emits a sound wave. But the sound wave only comes back to the bat, so he only hears the sound wave again 2 seconds later. Now, obviously, if he is flying at a constant speed to the right, due east, he's not going to be in the same spot when the echo comes back to him. So during those 2 seconds, he actually covers a distance of 6 meters. So let's say that 2 seconds later, he is at this point, meaning that the distance that he would have covered from his starting position to that point would be 6 meters. So this is going to be significant, right? We're actually going to come back to this a little later. For now, what we're going to do is we have speed and we have time. I'm going to work with that to calculate distance, but it's not x, okay? What we need to solve for is x. But we're just starting off there first. Speed is equal to distance over time. Now, speed was given as 340 meters per second. We're going to leave distance as our unknown. Time, I'm working with 2 seconds. Taking this 2 and multiplying across, we get distance as 680 meters. So what exactly does this distance represent? This is the distance that the echo traveled. Okay, this is the distance that the echo traveled. So that's important. I'm just going to label it that way. Now, how do we know that? It's because we used the time for the echo. He heard the echo 2 seconds later. So we want to know, in those 2 seconds, how far did the echo travel? So we're using speed is equal to distance over time, and the 680 meters is the distance that the echo traveled. Now, why is this significant? Because initially where the bat was at this point, the echo had to travel x meters. So let's write that down. So the echo had to travel x meters. So basically, the echo was emitted, right? And the echo traveled all the way to the wall, which was x meters. Once it hit the wall, it was reflected off. And when it was reflected off, it traveled up to this point. Now, what is that point? That point is going to be x minus the 6. Because this is where the bat was when he heard the echo. And he traveled 6 meters. So we are going to add x plus x minus 6 is equal to 680. Now, if you're still confused about this, the 680 meters represents the distance that the echo traveled. And we know that to cover that 680, The echo traveled the entire distance x meters, and then it traveled back, but when it was received by the bat, it was at this point, which is x minus 6. So x plus x minus 6 is equal to 680. Now let's solve. So gathering like terms on the left, we have 2x. Taking the 6 over to the right, we're going to have 674. And dividing throughout, actually that was going to be 686, right? Because it went over and the sign changed. That was a mistake. Then dividing throughout by 2, x ends up being 343 meters. So this represents the initial distance that the bat was away from the wall. That was the distance between the bat and the wall. Right, next we have a piece of information given. It says the wavelength of the sound wave emitted by the bat is 7.56 times 10 to the minus 3 meters. Remember, that is lambda. 1.4.1 says use suitable calculations to determine whether a human ear will be able to hear this sound. Now, obviously, to do that, we need to calculate frequency. So let's do that first. Using our formula, V is equal to frequency times lambda. We know that V is 340. Frequency is unknown. Okay, that's what we need to get. And lambda was given as 7.56 times 10 to the minus 3. Now to get F alone, you're going to divide both sides by the 7.56 times 10 to the minus 3. And what you end up with as frequency is 44,973.5 hertz. Now this is beyond human hearing. We know that humans can only hear up to 20,000 hertz. So this means that the sound will not be heard as its frequency is greater than 20 kilohertz, which we actually need to conclude, okay? That is why it's 4 marks. There was 3 marks for your calculation and 1 mark for your conclusion. The frequency is greater than 20 kilohertz, which you know is 20,000 hertz. Therefore, the sound will not be heard by humans.